All right, well, welcome everybody to the VREF Roundtable on Avionics. We've got a fantastic agenda for you today. And joining us, we have Mr. Ken Dufour, Mr. Jason Zilberbrand, Mr. Neil Fulbright, and Dr. Andreas Grossel. Gentlemen, how's it going?
Good morning. How are you, Chris?
Good.
And before we get too deep into everything, just some quick housekeeping. Can everyone see and hear us okay? And for our agenda today, we're going to deep dive into avionics. We'll start off with Avionics 101 and then transition to how to value avionics. We'll also be talking about upgrading and financing. We'll be getting a global avionics overview and then talk about the future of avionics. And to kick things off with Avionics 101, Neil Fulbright, please take it away whenever you feel like it.
All right. Thank you very much, Chris. Avionics, we just talk about some terms and go over some common equipment. And we'll start off with avionics and what it means. Avionics is actually an acronym. It stands for aviation electronics. It can be anything on the airplane, electrical, electronic. However, we usually think of it for the autopilot, navigation, communication. Now, with communication, we got connectivity. Here's some of the topics we're going to briefly touch on: ADF, DME, some transponders, the Mode A, CNS, nav and comm, GPS, ADSB, glass flight decks, how to tell the difference between first gen and second gen. Some synthetic vision, gyros, autopilot, and yaw damp. All right, let's start it off with the old non-precision. This is one of the first forms of radio navigation, ADF. It's a non-precision type. Basically, a receiver is using an antenna technology to determine where a transmitter is. Of course, some of the very first forms of radio navigation was four-course or AM navigation for some of you old guys like me. DME, distance measuring equipment. So distance measuring equipment, these DME ground stations are going to be co-located with either a VOR or a localizer so that we can determine the distance to a ground station or the runway. It calculates distance in nautical miles, and from changes in that distance, it can determine ground speed may go to the station or time to the station. Transponders. So here's a big topic, transponders. And this begins, continues, I guess I should say, continues on with our pulse system, because DME is a pulse system form of navigation, communication, and transponders are as well. They use pulses to interrogate and to reply. So we have Mode A. Mode A is our identity. This is a squawk code that the flight crew would dial into the front of the transponder. And then we have Mode C, and Mode C transmits pressure altitude. Pressure altitude is based off of a standard day, 2992 inches of mercury or 1013 millibars. Then we have Mode S, and Mode S is selective interrogation. That's what the S stands for, and it transmits a unique ID. Now, it's usually the tail number. It can be the flight ID, and it's going to exchange information of position, heading, altitude, things like that. And if you have TCAS, you're going to need a Mode S transponder. Mode S transponder is integral in the interrogation of other airplanes. VHF nav. So VHF nav is going to be VOR. It's going to be localizer, and it's going to be glide slope. So VOR, very high frequency omni range. It's used to determine a bearing to or from a ground station. And then we have part of the ILS. We have localizer and glide slope. And localizer gives us left or right guidance for the runway center line. And the glide slope will be a paired frequency of the localizer, and it gives us a vertical guidance about a glide path, usually 2.5 to 3 degrees to the threshold of the runway. VHF comm is just what it is, voice communications. We use amplitude modulation in aviation, and other things you might be familiar with, frequency modulation, but in aviation, it's amplitude modulation. Air to air, air to ground. Global positioning system. So global positioning systems, from a user standpoint, is the easiest form of navigation. It really tells us where we're at. So it gives us a present position, and that present position can be updated on a mapping system, and we can see where we're at. We also can input a waypoint, and GPS will give us guidance to that waypoint, altitude, and direction.
So does GPS, Neil, does GPS replace your ADF and DME and Mode A and Mode B, or is this redundancy?
So you always need redundancy, and this is one of the reasons why you know, ADF is still around, although it's non-precision, but it's one of the reasons why we still have VOR, why we still have localizer, why we still have glide slope. So Loran went away a few years back, and that was a backup to some of these, but now GPS is, well, the VOR localizer can be a backup to GPS, or it can be the other way as well. So 121 carriers can't and don't use GPS as a primary source of navigation, but in general aviation, you're seeing GPS used as a primary source of navigation, and VOR, localizer, glide slope, kind of secondary to that.
So when you see people buying brand new aircraft and they find that they have to order some of this old technology, or it is even still available, that will never change. It's not about job security. It's actually about redundancy, correct?
It's going to be about redundancy. You have two different systems. So one of the nice things, yeah, exactly. It's about having two different systems. So if GPS fails, and GPS is actually kind of a delicate system. There's been cases of outages with GPS and the accuracy of GPS. So you do want some form of backup, and you get into like the bigger 121, and they'll actually be using inertial reference systems as their primary, which GPS can cross-check, but they'll use inertial reference systems for the primary because inertial reference systems don't require any outside influence. Like a GPS requires a signal from a satellite. VOR requires a signal from a ground station. Localizer, a signal from a ground station. And glide slope the same way. So they'll use inertial reference systems, and they're completely independent. The same reason that they'll use TCAS. They'll use TCAS because it's self-contained on the airplane, and it's not dependent on ground stations, you know, communicating back and forth with the airplane. Same thing on 121 with weather radar. Weather radar, they have their own onboard system, so they're not relying on like FISB information from a ground station.
So Neil, the more sophisticated the airplane, you have more of a blended solution. Avionics, whether it's inertial, VORs, GPS, they all blend into a flight management system, and then that what guides the airplane.
Yes, correct. So we get into the flight management system, start getting a little autopilot, and we'll talk about that in just a little bit. But yes, that's absolutely right. The for example, the inertial reference or the GPS will be telling it what its present position is, and the flight management system knows what route we put into it or where we want to go, and it gives us guidance to that based off of where we're at, which way we're headed, what our altitude and speed is. I mentioned briefly that it's used for cross-checking inertial reference system positions, also an integral part of enhanced ground proximity warning systems. It's one of the reasons why, that's where the E came from, actually, was the GPS part of it could tell us what was in front of us based off of a database from enhanced ground proximity warning systems. Ground proximity warning systems, before the E was added, before the GPS was added, were only looked at what was below us. We used radar altimeters to look at what was below us and changes in that. Was the airplane descending? And then you would get, you know, don't sink, or was the terrain coming up to the airplane, and you get call outs like terrain, terrain, terrain. And of course, with ADSB, automatic dependent surveillance broadcast, you have to have GPS. That's the position determining equipment that ADSB rebroadcasts out to all the other airplanes and the ground stations. TCAS is a traffic collision avoidance system. So TCAS uses Mode Stransponders to interrogate aircraft. So it actually is acts like a flying ground station. It interrogates other aircrafts and look for their relative altitude. Remember the pressure altitude that I mentioned earlier. So all of the airplanes are based on they're going to output their pressure altitude. It doesn't really matter if that's their actual altitude. What is important is what is their relative altitude to your aircraft or other aircraft. And then TCAS will give, TCAS 1 will give traffic advisories. You know, there's traffic. Or if you have a TCAS 2 system, you can get resolution advisories, which gives us a vertical resolution or vertical profile to fly based off of feet per minute to avoid the closest point of approach. The big one, ADSB, this was the big one this year, 2020 mandate. ADSB transmits position, velocity, altitude, of course, and identity to other aircraft around it and to ground stations to be rebroadcast on rebroadcast from the air traffic control system. So ADS-B out was the mandate. ADS-B in. So ADS-B in this country, in the United States, you can get ADS-B in through 1090 extended squitter. This is the Mode Stransponder. You can also get it from a universal asynchronous transceiver, a UAT. That operates on 978 megahertz. So either one of those you can get in. However, if you have the UAT with the 978, you can get free weather. If you are using the transponder, of course, both of them give you traffic, but you do not get free weather, free FISB information from the ground station. But if you have the UAT, you do. So that's kind of a nice little feature of adding ADS-B in. It's one of the reasons why we had so many early adopters to ADS-B for 2020.
And ADS-B out was a requirement 1 January of this year, correct?
Absolutely, it's a requirement to fly in certain airspaces. There is was a Class G that you can fly without ADS-B, but there's not much of that. So yes, ADS-B out is a mandate from January. Glass flight decks. So let's get into the glass flight decks. The first generation systems, these were dedicated systems. As you can see with this picture, there's no glass for the engine information. It's really EFIS, which is electronic flight instrument systems. And then this one actually has an MFD, but the first generation systems are easy to identify because the displays are one on top of the other. The EADI, the E stands for electronic, and the EHSI, horizontal situation indicator and attitude direction indicator. And then on this one, we have a multifunction display to handle some of the things that because there's not a lot of real estate on these early version displays. So this MFD would handle weather radar, some nav data, and then some checklists. The first generation dedicated. Second generations are integrated systems. So now everything is starting to talk to everybody else. You can move the information around on these displays as you need to for emergency. There are some systems where you can do it for convenience. They're integrated, meaning that all of the components are sharing all of the information. And now we have a primary flight display. Primary flight display, PFD, is where you'll normally hear it, is a combination of your EADI and EHSI. And we have a nav display. The nav displays display our route and weather and traffic and things like that. And with the second generations, we added some engine indication. So we can get that primary engine indication up there. And also some crew alerting. So annunciations to faults and failures on the airplanes, or even if something's starting to drift out of its normal operating range. Second generations, newer generations, I should say, they may have a HUD, heads-up display. It is degree for degree conformal to the outside environment. It is frequency selective, meaning it only reflects one frequency that we interpret. If you see the slide on the right where you can see the green, that's the only frequency that it will ever reflect. Everything else would pass through. Otherwise, it reflected all of it. It'd just be a mirror.
So Neil, with HUD, is this a good example of technology that's come way down in price just over time? Is this a good example of that? Of how?
Oh, definitely. When these first came out, just the install part of them alone was very cost prohibitive to do. So, and now, although the display technology is not that complex, some of these are still using like CRTs. Or even at the newer versions, they're using LCDs to reflect that image. So in that part of the technology with the LCDs has driven the cost way down on these. And so we're seeing them more and more. And it's a great safety feature too, because from heads up, because now that we have heads up, we also have, now that the regular displays that we're used to, we call heads down. But you'll lose about 3 seconds of focus going up and down, back and forth, where now you don't have to do that with the heads-up display. Synthetic vision. So synthetic vision is also another nice safety feature. Synthetic vision is not, it's not using radar or anything to look out there. It's actually coming from a database. The database is based off of elevation plots and topology charts. And it is polygonal represented on the screen as to what is in the database that would be out in front of you. So to show you the terrain, obstacles and obstructions out there. If they came out and put something up overnight, it's not going to show up on the screen. So it's to refresh that database is kind of very important. Gyros. So the gyros. So where we get our attitude information from, or in the case of inertial reference systems, we get a lot of information from gyros. On the lower cost end, we have the rotating mass gyros. Their principles are rigidity in space. On the upper end, we have the inertial reference systems that use laser ring gyros and accelerometers. And right in the middle, we have attitude heading reference systems. So let me back up a little bit to rotating mass gyros. If we have rotating mass gyros, we get our attitude information from that. We're going to need a compass system. So a compass system is going to have flux valves, just throw some of these terms out, flux valves, flux gates, flux detectors, magnetometers, something to sense the Earth's magnetic field and give us a magnetic north direction. So they'll have that compass system as well as the rotating mass gyros. The inertial reference systems, I kind of mentioned this earlier, they don't rely on any outside influence from the airplane. So inertial reference systems don't have a compass system. They don't sense the Earth's magnetic field to determine magnetic north. They actually do this during their initialization, which is really basically their warm-up. They can determine true north. They know where they're at based off of the latitude and longitude that we put into these systems. And then from that, they can determine the true north heading of the airplane. Since they know where we're at, they know the deviation from true north to magnetic north. So it's all calculated. It doesn't rely on the Earth's magnetic field to determine a magnetic heading. So that's kind of a neat little feature of inertial reference systems, all self-contained. Then we go to attitude heading reference systems, right in the middle of these two, cost-wise anyway. The attitude heading reference systems, they will have a traditional compass system, just like the rotating mass gyros had, and then they'll use some other, in each manufacturer is a little bit different as to which type of gyroscopic sensor they use, or angular rate sensor. And for example, one of the more common ones, I'm not going to mention the manufacturer, but they use a MEM sensor, miniature electronic micro, MEM sensor. I messed up that acronym. But it's kind of the same sensors that you have in your telephones that determine the orientation of your telephone. So when you rotate your telephone, same sensors that they use those for gyroscopic or angular rate sensing to determine, changes in the aircraft's attitude. Autopilot. So autopilot's really a collection of systems already in the airplane. So we have some type of gyro system. We have some type of something that gives us, our attitude. We're going to have air data information. So something that gives us our airspeed, altitude, vertical speed, temperature. We're going to have VHF nav. So we need inputs for VHF nav, localizer and glide slope, things like that. So those are the normal systems we have on the airplane. We put those together. We have a flight control computer. So the two major components really in autopilot would be, let's say the computers, and are going to be a flight control computer and a flight management computer. Flight control computer handles your normal modes of autopilot. So, attitude hold, altitude hold, things like that. And then your flight management computer is going to, that's going to be flying routes. So based off of a database, we input where we want, origin to destination, via waypoints, and it manages the flight for us. And the flight management computer actually tells the flight control computer what to do on bigger airplanes. So, and then
another example of just technology advancing quicker than most people can adapt. So you tend to see a lot of new autopilots continuously released to the market, correct?
Correct. Yeah. And then one of the nice things is you get pre-programmed routes that you can put in these things. So if you're doing routes over and over, it's easy. Just plug it in, populates everything for you, and you take off and you actuate the autopilot, and it manages everything for you. YAW DAMPER system. So this is a system that may be a little confusing. So the yaw damper system really handles two different undesirable flight characteristics. One of them is Dutch roll. So an airplane, the swept back wings, high speed flight creates an instability in the airplane, and it makes the plane kind of the back of the plane kind of sweep back and forth, right? And when it does that, it eventually can get out of control and just roll right over. But in the process, everybody's sick in the airplane. It's very uncomfortable. So what it'll do is it not only reacts to that instability, but it also anticipates which way it's going to go next. So it creates a very, very stable flight. You don't feel it. It does a better job than the flight crew. The flight crew sitting up front. If they had to manage this undesirable characteristic, they would be reacting to it. By the time they feel it, everybody in the back of the airplane would be ill, very ill. So the yaw damp system may come from the autopilot system, but it's always thought of as a separate system. It has its own switches, so you can turn it on or off at will, independent of the autopilot. On larger airplanes that have larger fuselages, big vertical stabilizers, that fuselage twists in flight, and when it twists, it causes that vertical to move back and forth. And when the vertical moves, it'll make the airplane turn, and that's called structural modal oscillation. So on these larger airplanes, you can have the structural modal oscillations. They're so it's so critical to sense that they'll even put modal accelerometers in the tail of the airplane to sense that, instead of just trying to pick it up from the inertial reference systems. So yaw damp takes care of that role in structural modal oscillations for us. Connectivity, this is the big one for today, and this really kind of leads us into the future of avionics right now. So connectivity, voice data, and cabin communications, right? And we really have two systems for that, air to ground, or right now 2 common systems for it. Got air to ground. Air to ground is good for the continental US above 10,000 feet. So above 10,000 feet, you can get seamless connectivity from air to ground, 4G speeds. So pretty good, cheaper solution as far as data anyway. And then we have satellite-based systems. So we have LEO systems. LEOs are going to be your narrowband. This stands for LEO, stands for low Earth orbit satellites, and that's going to be where your Iridium system type are going to fall. Voice, some data, not broadband solutions. So not right now anyway. There's a couple of systems out there that are coming up with that. So we have the medium Earth orbit. Those are mostly reserved for research and military. And then we have the most common, besides the Iridium, we have the most common, which are the high Earth orbit, or we tend to call them, you tend to hear GEOs. And that means geostationary, stays in the same relative spot in the sky to where we're at on all times. And that's going to be your broadband solutions. Inmarsat and Telesat and Viasat are the big players there.
I know that a lot of business jets now, a lot of international long-range aircraft are having ATG and some sort of geosatellite system installed. But at what point in the future do these systems actually merge and allow for, kind of a one-size-fits-all type of solution for connectivity? And is some of that is 5G related versus, existing infrastructure?
Right. So that would be nice. And the simple answer to that is they're different manufacturers. So they're going to hold on to their technology to have, they have some of those Inmarsat, they have their own satellite systems up there. So they want those used to have air to ground and satellite all in one. It's going to be based off of a company. It's going to, is a company going to have an air to ground solution and a broadband geo solution all in one? Then that's when you can get it.
So this is important. I think this is an important subject for people, because I don't even think a lot of people in our industry know this, but you're really talking about branding more than you're talking about solutions, right? Because most of these satellite companies have invested a ton of money into putting their satellites up into orbit. And that's really what you're talking about, is which infrastructure are you going to align yourself with? It's not really which one is different, right? It's a Pepsi versus Coke. Is that a better way of putting it?
In the satellite arena, yeah, it can be. And then you're also going to have a provider. Just because you're using an Inmarsat satellite, you may be using, let's say, Satcom as a provider for that data.
So you're really relying on which manufacturer the OEM aligns with at the time the aircraft was manufactured.
On new aircraft, yes.
Okay.
And you know, to get a complete total solution, air to ground, iridium, in, you know, Inmarsat and Telesat Viasat, get to have a complete solution, you're well over $1 million in a system, easily over $1 million in the system right now.
And so from a depreciating standpoint, these systems all depreciate fairly quick. And I know I get asked this.
Very fast. Yes.
Can you explain why avionics depreciates and how much of it can be compared to like consumer electronics, like people buying TVs and laptops versus networking systems that they might be accustomed to seeing in their office?
Well, that's a good association to consumer electronics, but with the exception that, you know, the technology in aircraft, it's limited by, you know, how can it get certified. Once it's certified, now you can install it on the airplane. But as new technology comes out, it doesn't come out in a set schedule. So take your you know, take your phone. A new one comes out every year, right? So we can that is kind of set. We know that a new one's going to come out, let's say, just say in September, right? So the new ones come out in September. We know that the old ones are going to be worth less at that point. In aviation, that's not necessarily how it is. It can be dependent on utility. You know, do you need this piece of equipment on the airplane, as opposed to comparing it against an airplane that doesn't have that equipment? Then it's going to have value there. But the minute that something else comes out with better technology, better features, cheaper cost, then it almost makes the other one obsolescent.
But you also have a learning curve involved with new technology, right? So you have a generation issue as well, which is why you still see older systems installed in aircraft, correct?
Well, and the older systems still work, and they work good. Yeah.
But I think I think it's interesting if, and certainly you or Ken could talk about it, is from a student pilot standpoint, why you still see older systems installed in aircraft, why they just won't go away.
Well, the older systems are there because you know, they were initially certified that way with the type certificate, and they'll be there for a while. And it's cost, some cases on older airplanes, is cost prohibitive to change all of that out and reinstall, you know, Garmin G1000 or glass systems. So you're still encountering that we have the older airplanes, and as you all know, that we track all the old airplanes in VREF, and a lot of them will be around a long time, and not a lot of those will be upgraded to new technology. So if you're not familiar with the older technology, but you've learned on the newer technology, again, it's another learning process or another student process that you have to teach those students how to fly, as we call them sometimes, steam gauges or traditional round gauges, which are, you know, still prevalent, but a lot less sophisticated than the stuff Neil's been talking about.
Well, and from a valuation standpoint, I think we all have our challenges every day in trying to figure out what some of these packages from some of these avionics manufacturers are worth, right? Today, you have a dozen options for what you can put into a GA aircraft versus what, 30 years ago, maybe 2. And that would, right? So there's a lot. You can't just go ahead and start making willy-nilly decisions about what you're going to install, especially if you're trying to do, as Neil was talking about, a fully integrated panel. So there's so much freedom of choice today. And I think that's part of why there's so much confusion in the marketplace. You know, what company do you align with? And then are you forced to deal with them forever? You know, that's the other issue as well, right? So you have software, you have upgrading, and then you have the ability to do software updates. And certainly you guys know how long it takes to do software updates in the older FMS systems. And so how much of this is too much freedom of choice versus people just not really understanding their long-term, you know, approach to when they start upgrading avionics?
Yeah, exactly. You have to watch. Another consideration is you need to watch which manufacturer that you're choosing, because some of them don't play well with others. So you can't buy one piece from this manufacturer and then one piece from this manufacturer, one piece from that. Excuse me. Some of the ones that are integrated, you're going to have to buy their whole suite to get all the features that you want, or you can't just piece it together from other manufacturers like you could do with some of the older, as Ken said, steam gauge radios and instruments.
Well, and then you're also getting into like Garmin, for example, right? Everything that they do is proprietary. So you'd have to rely on their panel mounts, right? The whole kit and caboodle, and then you have to deal with an authorized dealer network as well, correct?
Mm-hmm. Yep, exactly.
So
A
can
great
you
example.
talk about how you go about determining, and I think Garmin is a good one just because they are the 500-pound gorilla, so to speak, in GA. And I think people are very accustomed to seeing various models out in the market. But how do you go about valuing, you know, for example, a GNS 430 or one with WAS or one without or a 530? How do you determine how much shelf life, so to speak, is left on a unit when there's been, you know, 10 versions that have come out since, or it's not the latest, you know, and greatest on the block anymore?
Yeah, so, and you kind of almost said it there yourself. If you got 10 versions that came out after it, you're down to nothing really on that. You know, it's really going to be dependent on where it's at in the timeline right now. So is this the newest system that's out there? If it's not the newest system that's out there, there is a newer system. So you're going to be, you're going to lose value the minute that something else comes out that's greater and, you know, better.
We also get asked this all the time, but avionics that's been removed and tagged versus something that's installed, is there a difference in how you go about valuing something as a standalone versus integrated inside of an aircraft and operating?
Right. So well, that just opened up a can of worms. So
Right. Which is why I brought it up, because I think this is one of the big issues that we all deal with every day, right? And
yeah. So was it just as removed, or, you know, did they just remove it? Was it as removed serviceable? Is there documentation that goes with that? That all of that plays into just the value of the one you removed. You know, what was it on? How much time did it have on it?
just because it's serviceable does not mean it's going to be supported. And I think that's really important that people understand. You're not buying something with a warranty. You're not buying something that's guaranteed to have somebody answer their phone if you need troubleshooting. It's still consumer electronics, correct?
Yes, it is. Right.
So when you go on eBay and you buy a 10-year-old radio and you take it home and put it in your airplane, you know, is that necessarily the best approach to installing avionics?
Nope. that's just the easy answer to that. Nope. And then depending on what it is, you know, you get into transponders and things like that, and they have to be certified every 2 years.
So going now from small airplanes to big airplanes, because I think that there's a lot of solutions in the GA world, but when you start talking about business jets primarily, you really are at the mercy of A, the original equipment manufacturer and their vendors, right? And then B, whoever has gone out and gotten an STC for some sort of aftermarket solution. So I know people ask all the time, how do we value, you know, aircraft that have gone through, you know, major upgrades and having, you know, old panels removed and brand new glass cockpits installed. And, but I think for the most part, you know, people's questions are, how do you compare it to the original installed equipment? Is it, you know, do you deduct for taking all that stuff out and going ahead and selling it off part by part? Or does, you know, somebody who's doing the STC, and do they take that all in on trade and then, you know, try and work out the numbers so that it's not so, I guess, you know, financially, you know, taking such a big hit on the owner of the aircraft? And then I guess the last question, you know, for Ken is, can you finance this stuff? Do people actually go ahead and go to a bank and borrow money to upgrade their avionics in a business jet that could easily cost over $1 million?
In the past, you know, when we were re-engineering airplanes, it was a great time to redo the flight deck and upgrade the avionics at that time. We, as Neil said, with an STC, a supplemental type certificate, we don't quite see that as much in the modern day, because a lot of people are not re-engineering airplanes and they don't go through that massive of an update to do that installation. So we see less of that. But if you do want to upgrade some avionics, they are financeable. You just have to go to the financial institution, and we'll see it a lot in the general AV world, where the AOPAers and their financiers, they want to take an older generation airplane and they want to update it with new avionics, which is obviously logical, and they can get expensive depending on you know, what you're trying to install. So they will accept, you know, some finance and do some terms for that. So you need to check that with each financial institution. And of course, it will add value to the airplane. There's no doubt about it. So that's another consideration when you're doing it. And one of the things we see a lot of ask, and what Neil's been talking about, is how do you value a new install, especially on the subject we're just talking about. So what I like to consider is I like to consider the total cost of the avionics, what I call boxes on the hangar floor. What's the actual avionics costs? And then I would like to consider what the installation cost is. So what I'll traditionally do is take both of those total costs and add them together. So let's say I have $90,000 of avionics and I have $10,000 of installation. Obviously, it gives us $100K of total cost. Excuse me. So what I normally recommend to the financial institution is that we'll make an allocation of basically 90%, 80 to 90% of that total cost. So that would be 90 plus 10, 100. So 80 to 90% of that, you know, $80,000 to $90,000 would be an add to the bottom line of the aircraft. Most of them are willing to accept that. Conversely, to look at it differently, we do the same thing with installation of interior and cabin electronics. We do the same total cost of one to the other, and then we take less of a percentage because those that paint interior can be quickly changed by the next owner, operator, wife, husband, significant other, etc. So we usually will take somewhere from 60 to 70% of that total cost factor to add to the bottom line to give you a comparative of what we do with the avionics, especially if the avionics / electronics are going to stay with the airplane. They enhance safety, they enhance operational capability of the airplane, and they're not going to be removed too quickly. So that's a big advantage to have them installed.
And next up, Andreas Grassel is going to give us a global perspective.
Well, thank you, Chris. Maybe everybody knows that we appraisers have to work according to standards. For us in Europe, it's the International Aviation Standards, and they state quite clearly that we, the appraisers, have to have the knowledge in which markets the aircraft trade and what would be the purpose of evaluation. And this is very, very important because although we are supposed to work in a global market, there are local differences simply because there are still no global, there is no global standard for equipment that is required to operate an aircraft. The FAA, the EASA, Transport Canada, the Chinese CAA, the Russian SCAA, they all have different standards and requirements, and these different requirements influence the value of an aircraft. Simply because if you have some equipment, some expensive equipment installed in an aircraft that is only required in a local area, in a local airspace, the prospective buyers in a different market like the US will not honor this installation because it's not required to operate the aircraft there. To give you some prominent examples, ADS-B. The FAA, as Neil already told us, requires it for all aircraft, but for smaller aircraft, a UAT solution is available. EASA, on the other hand, requires multilateration for all equipped aircraft, but the requirement is only for aircraft above 5,700 kilos max takeoff weight. We call it takeoff mass in Europe, or that's roughly 12,500 pounds, or for aircraft being able to make more than 250 knots through airspeed. So for small aircraft, you do not need ADS-B out in Europe, and there is no intent by EASA to one day introduce such requirement. Talking about ELTs, maybe you know EASA requires a 406 megahertz ELT for all aircraft below 20,000 kilograms max takeoff mass. Why? The airlines didn't want to invest because the larger aircraft usually have other means of communication. And except for some bad examples like the Malaysian crash, you usually should know where a large airliner is in space. So small aircraft or aircraft below 20,000 kilograms need a 406 megahertz ELT. In the United States, you can still operate the old 121.5 243 megahertz ELTs, although in the US, you're no longer allowed to import or install these ELTs. You are still allowed to operate it. But an aircraft with a 121.5 ELT from the United States, which is sold to Europe, requires re-equipment, and this is costly. So a prospective buyer will deduct from the value the cost of the installation. 8.33 kilohertz spacing on the COM radios. EASA requires all aircraft in all airspace to have this 8.33 spacing. The FAA doesn't mandate it, although this is no longer of real concern because the modern GPS Garmin installations, they all have the ability to switch between the 25 and 8.33 spacing. Area nav, a very important point. Most airspace in Central Europe no longer has airways. You have point-to-point navigation for hundreds of nautical miles. So without an area nav, certified area nav aircraft, you cannot fly IFR in Europe any longer. They decommissioned the VORs, the DMEs. In the FAA world, the airway system is still available. So an aircraft that's pretty much able to fly IFR in the United States will not be able to operate IFR in Europe. This is an influence on the value. Someone who buys it has to reinstall expensive equipment. Even more complicated for large aircraft, cockpit voice recorders, flight data recorders. The FARs are basically based on the number of passengers an aircraft can carry, and then you have the requirements. In Europe, we have this infamous regulation 965 from 2012, which is 1,100 pages, not only FDRs, but other equipment, that has a very complicated system, a combination of the kind of operation, commercial, non-commercial complex, non-commercial, non-complex, weight, passengers, required flight crew, date of type certificate. And depending on this combination, you have different requirements for flight data recorders and cockpit voice recorders. And there's also the question how many channels are recorded. EASA is increasing this, although ICAO is following suit. But there is still a lot of differences. And here, one of my favorites, that's the STCs. That the picture that you see here is what I call a poor man's glass cockpit. This is a very common installation in Europe. This is a 172 with an Aspen PFD and a Garmin GTN 750. This is installed based on an STC that was created by a maintenance shop in Germany. They got it certified through the German Luftfahrtbundesamt with EASA, but this is not certified in the US. So if you want to bring that aircraft to the United States, you have either to find a DER who is prepared to issue a airworthiness certificate, but from my experience, this usually is not the case, or you have to retro-engineer the whole installation and get it certified by the FAA. And the same is true from the FAA with STCs that are not validated by EASA, which is even more complicated and more costly. So all these expensive installations can be of no value in a specific market, either because it's not required there or it is not certified. So that's why it is very, very important to get good advice and to know where the aircraft will trade and what requirements have to be met in order to get the aircraft certified. So if you have any questions on this, in particular in regard to Europe, just give me a call, send me an email, and if I'm not the right person to answer it, I have a lot of really knowledgeable people at hand who could answer you these questions and check for you if this aircraft could be re-registered in a different jurisdiction at reasonable cost or not. So for us as appraisers, it is sometimes really, really hard time to assess the value of an aircraft that has to go from one jurisdiction to another.
Excellent. Thank you so much, Andreas. And we'll have the contact information available for everyone who is interested. And Neil, where can people reach you to if they have any questions about avionics?
So my phone number is 386-316-3551. And my email is infulbright@vref.com. So infulbright@vref.com. I'd like to talk just briefly, and this is going to be quick, about the future of avionics. And really the future of avionics is going to be seamless and continuous broadband connectivity. This is where everything's going. Our avionics technicians are now being tasked to be basically IT administrators. You know, our office, with the way things is, this is our office, and we need these to work seamlessly and continuously, no matter where we're at. And so that's where the future is going to go. That's where it's headed. We need to be connected continuously, no matter where we're at.
To use with your VREF, there's a couple of FAA publications that may be beneficial to especially general aviation type audience. One is called Plane Sense, and we could probably link it down, the FAA publication number. It's called Plane Sense General Aviation Information, which has a wide spectrum of from purchasing an aircraft and owner's responsibilities and requirements. And one that's even more in depth is called Advanced Avionics Handbook from the FAA, which is basically a learning guide of how to get you up to speed on flying some of the newer generation stuff that Neil and I have been talking about here, the new glass and how it navigates and how it works. And those are two great publications to review as you consider avionics purchases or upgrades.
Fantastic. Well, thank you, gentlemen. This was terrific. We'll get to the Q&A. So if you have any questions, please put those in the chat.